Hello, Worthington Juniors reviewing for the MCA. This MCA lesson is all about circles and their central angles and their arcs. So first, let's define what all of those ideas are. So we're going to start with central angle. A central angle is an angle whose vertex is at the center of the circle. If you notice in this picture down here, we have angle APB. P is the center of the circle, and therefore this is a central angle that we're used to seeing. However, what we are not as used to seeing is something called a minor arc. It's part of a circle whose measure is less than 180 degrees. So this would be an idea of a minor arc because its measure would be less than 180. Whereas a major arc is a part of a circle that measures between 180 and 360 degrees. So the major arc in the picture would be arc ACB. Notice both the minor and the major arcs start and end with A and B, but when I said them, I said the major arc with an extra point so you knew where we were going. Next is the idea of a semicircle. That's an arc whose endpoints are on the diameter of a circle, so it's going to go halfway through. What we know about a circle is that it adds up to 360 degrees, so the semicircle, which would start and end at a diameter, is going to be 180 degrees always. So, naming them. Kind of said a little bit about this. The minor arc is going to simply be called AB. That's how we name this, minor arc AB. Starts at A, ends at B. Whereas the major arc is actually, and semicircles, are going to be named using their endpoints plus one other point on the arc. For example, this is named arc ACB because we're including point C, so we know the difference between that minor and major arc. Alright, when finding measures of them, what you need to realize is that a central angle and its corresponding minor arc are actually congruent. So, notice angle GHF has an angle of 60 degrees, and therefore the minor arc GF would also have a 60-degree angle. Again, semicircles, 180 degrees, and major arcs. If you're looking for major arcs like arc GEF, what we would actually do is simply take 360 minus the little minor arc that we're not including. So again, to find GEF, we're going to take 360, which would be the whole circle, and subtract this minor arc that we're not including. So to find major arcs, we are usually subtracting from 360. Now, one other way, or one other idea that you could use in order to find the measure of an arc is to simply add arcs together. If you wanted to know what's the measure of arc ABC, you could simply take the measure of arc AB and combine it with the measure of arc BC to get the total arc length. Alright, let's try an example. This one gives you one picture with one angle. They tell you one central angle, angle CAD. This central angle is 148 degrees. From that, we're going to be able to answer a few questions about their arcs. First is, what is the measure of arc CD? So arc CD actually corresponds with this central angle, and therefore CD, that minor arc, is 148 degrees. Done. Okay, now, we actually have to do one that's a little bit tougher than that, and that would be arc CDB. So if we draw CD going through D all the way to B, we have this major arc. Okay, now, if we wanted to subtract from 360, as we talked about before, we could. However, we'd have to subtract arc BC, and, well, we haven't found that yet. So let's try another idea. Let's use the idea of adding arcs to get a total arc. So what we can do is remember that CD was 148, and if you notice on the other side, D to B is actually a semicircle. It's half of a circle. So this is 180 degrees. So again, what we know is that this much is 148 and this much is 180. So what we're going to do is we're going to take 180, combine that with 148, and we get our angle of 328 degrees. So the major arc CDB is 328 degrees. Now, to find arc BC, we can actually use the idea of subtracting from 360, because actually the whole circle should be 360, and we know this is 328, so how much more do we have to go? Well, let's subtract. Let's take 360 and subtract 328, and what we're left with is 32 degrees. Now, is that the only way you could have solved for arc BC? No, there's actually one other way, and maybe some of you saw it, so we're going to go ahead and talk about it for a second. B to D is again a semicircle, so this whole piece is 180. But notice from C to D is 148 of it, so actually you could have taken 180 and subtracted 148, and you still would have gotten your 32 degree angle. Same idea, they both get you the correct answer. Alright, some more theorems about circles. First is that if you have this in the same circle or in congruent circles, two minor arcs are congruent, meaning arc AB and arc BC are congruent if and only if their corresponding chords are congruent. If you remember, the definition of a chord is a segment whose starts and ends on the circle. So if we're talking about arc AB, its chord would be chord AB. Starts at A, ends at B, that line there. If those are congruent, then the minor arcs are congruent, and vice versa. If these minor arcs are congruent, then those segments are congruent. Next is all about the diameter. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Actually, this word bisects is really important. What we should remember is bisects. When we talk about bisecting a segment or an angle or whatever we're doing, when we bisect, we split something in two equal halves. So what this is saying is if the diameter is a perpendicular, so we have our 90-degree angle, then it's going to bisect that chord. Bisect means split it into two equal halves. So the length of DE would be equal to the length of EF. And if we remember, if those lengths are equal, then that means those minor arcs are equal. So minor arc DG and minor arc GF would also be equal because those are equal. And lastly is that if one chord is perpendicular or is a perpendicular bisector of another chord, then the first chord is the diameter. So if we have a perpendicular bisector, this segment JK is both perpendicular and bisects this other segment, then that means it's automatically a diameter and it is going through the center. Its length is the length of the diameter. So let's try a couple of examples. This one wants you to find the measure of minor arc BC. All we know about minor arc BC right now is that it is 2x plus 48. But if we look closely at the pictures and see the notation that they left behind for us, is that they told us this chord BD and this chord BC are congruent. So if we think back to our theorems, if we have congruent chords, then that means we have congruent arcs. So actually arc BC would be congruent to arc BD. Well, I don't know the exact length of BD, but I have another expression for it. So what I can do is set arc BD equal to arc BC, solve for x, and then go back and find the right length. So here we go. Let's write our equation. We know that 3x plus 11 is going to be equal to 2x plus 48. Now, to solve, we're going to get our x's on the same side, so we're going to subtract 2x from both sides. We'll be left with x plus 11 equals 48. Subtract 11, and we know that x equals 37. That's great, that's perfect, you did your math correctly. The issue here is that you didn't answer the full question yet. So, when you're taking your test, be really careful, go back, reread the question, make sure you answer the full thing, don't just stop at x. If they want to know the arc length, find them the arc length. So, what we're going to do is actually find arc length BC. BC was actually 2x plus 48, so what I'm going to do is I'm going to plug in 37 for x. So, we're going to take 2 times 37 plus 48. 2 times 37 is 74 plus 48. And we are going to be left with 122 degrees is the minor arc BC. It's 122 degrees. Okay, here we go. Next one. It says find the measure of minor arc ED. If you notice, different picture, same situation. We have ED and CD as congruent chords, and therefore arc ED is congruent to arc CD, meaning their lengths are equal. So let's set up an equation. 4x is going to be equal to x plus 78. Get the x's on the same side. We're going to have 3x equals 78. Divide by 3, and we get x equals 26. All right, again, have we actually answered the question? And the answer is no, because the question is, what's the arc length? So what we need to do is plug it in. Now, ED's arc length is 4x, so we're actually going to take 4 times 26, which tells me that ED's arc length is 104 degrees. All right, hopefully things are going well for you. Let's try one more theorem. This theorem says in the same circle, or in congruent circles, if two chords are congruent, excuse me, not if, but just simply two chords are congruent if and only if they are equidistant from the center. So to be equidistant, distance is actually defined by using perpendicular lines. So if this chord is the same length for me as this chord is, then they are congruent. Or if they're congruent, then these lengths should be the same. Okay, let's give this a try. This one says the length of AB is 12 and the length of DE is 12. So we have two chords that are congruent. If we go back up, if we know that the chords are congruent, then we know their distance to the radius is congruent, and vice versa. But in this case, we know chords are congruent, so we could prove distance to the radius is congruent. So what we know is this is 12 and this is 12. Therefore, from G to C, that should be equal from the same length as F to C. Those are going to be equal. Because these chords are equal, the distance to the center is equal. So let's keep reading. So we have equal chords, and we know a couple more lengths, and we are asked to find CG. Well, if this is 12, and this is 12, and from C to E is 7, we have to find CG. It's kind of looking like a little bit of a mess. Let's focus this just a little bit. What I notice is that from here to here we have 7. Okay. From D to E was 12, but if we think back to our theorems, if this is perpendicular, that means it's going to split in 2 equal halves. So if this whole distance is 12, that means from here to here is going to be 6. And then this one is unknown. However, this unknown, CF, is actually equal to CG. And that's what we're being asked to find, is the length from C to G. It's going to be the same as the length from C to F. We just have to find it. And if you noticed, we drew a right triangle. And to find one length of a right triangle, one side length, we're going to use the Pythagorean theorem again. So we're going to use the idea of a squared plus b squared equaling c squared. What we need to remember if you watch the Pythagorean theorem video is that c has to be across from the right angle. So let's go ahead and plug in our sides. We're going to have x squared plus 6 squared equals 7 squared. Let's go ahead and solve. X squared plus 36 equals 49. Let's get our numbers on the same side. So let's subtract this 36. We're going to have x squared equals 13. Solve for x, we square root. X equals, well, the square root of 13. That's the exact answer. You could type it in your calculator and get the decimal approximation, but root 13 is the exact answer. And now that stood, again, for the length of CF, but that is going to be the same length as C to G because of our theorems. Okay, let's try 2 more. This one tells me that A to D is 40 and C to D is 25, but we also have a few other markings. Notice these 4 lengths are the same, therefore the longer chords are the same. Therefore, keep that thought going, the distance to the radius is the same. Now it's not going to be the same as these lengths, but they're going to be the same as each other. So I'm going to use a 2 tick mark notation here. These and this are equal. Okay, let's set up a triangle idea again. Here's what we know. CD is 25. AD is 40. The whole thing is 40, but it's split up into 2 equal halves, which means this half is 20. And this one is unknown. And it's asking us again to find CG, but again, we know that CG and CF are going to be the same length because they are both the distance from congruent chords to the center. So, again, I've set up what should be a right triangle. Because if these chords are the same, and I want these lengths to be the same, then it should be a right angle because it's got to be perpendicular. Again, going back to your theorems, if these are equal length, then I know it's got to be perpendicular. If it bisected, it was perpendicular to the center. So, here we go. We're going to use a squared plus b squared equaling c squared again. A and B are going to be our x and our 20, and C is going to be across from the right